Once again, from the posh Physics 262 studios, we come with another lecture for Chapter 24. Chapter 24, I'm going to do one of the examples that is in your book for calculating the capacitance of just different geometries. I'm not going to do all of them. I believe there are 3 examples in there. I'm going to do the 2 concentric spheres. And I'm going to do it a different way than your book does. I recommend that you take a look at the way your book does it, and you compare it to what I'm doing. They aren't. Once again, we have different approaches, but the results are going to be exactly the same, which is one of the cool things about life, is that you can come at things from all sorts of different perspectives and still manage to get to the same result, even in politics, which at this moment it might not seem like that, but it works. Okay, so we have a sphere R sub A and a sphere R sub B. They are hollow, they are conductive. This has a charge of plus Q on it. This has a charge of minus Q on it. And what I would like to do is I would like to calculate the capacitance of this. That is, its capacity to hold charge. What is its capacity to hold charge? It's charge divided by the voltage. That's the definition of capacitance. However, I'm not going to approach it that way. I'm going to approach it a different way because we have already discovered something else. We have discovered that there is such a thing as the energy density of an electric field. And that energy density is 1/2 epsilon 0 E squared. This is the energy density, and then times the volume will give us the total energy of some configuration, whatever that configuration happens to be. My computer screen's about to turn off. I just want to see how far I can stretch. Yes. Okay. Excellent. All right. So this is an expression for the energy contained within this field. So this is what I'm going to do. I'm going to use this to determine the capacitance. Well, what is E? We're only concerned about the difference, the space between these charges, and you guys all know by now that we can use Gauss's law to determine that this is, Q over 4 pi epsilon 0 R squared. All right, and so, can I just then multiply that by the volume between here and here? Well, no, I can't, because this energy density, E, is a function of R. And so I have to do what I need to do to calculate this. I'm going to say this here. I'm going to say this is going to equal 1/2 epsilon 0 E squared d tau. You guys remember that I'd use the d tau abbreviation to represent the volume element here. And what is d tau? These are spherical coordinates, so you guys should know by now. 1/2 epsilon 0, this is the same as the integral E squared R squared sine theta d theta d r. And I'm pretty sure that's not all on your screen, so let me pull that back just a little just so you can see that once. But that's just a reminder of some things you already know. Okay, so now I just need to put in my form of E. So what is E? E is this right here, but now it's E squared. So what I'm going to have here is 1/2 epsilon 0. I'm going to go ahead and pull the Q, because that does not change, and the 4 pi epsilon 0, which also do not change. I'm going to pull those out here and square them, because this is E squared that I'm concerned with. And then in here, I have 1 over R squared squared. R squared squared is R to the 4th. And then what's the volume element? It's just, I'm going to rewrite it a little bit just for convenience's sake. Theta, d theta, and d phi. Okay, so you have seen this before, and you will see that there is no theta or phi dependence in here, and therefore we can just go ahead and do this integral flat out, and you guys know what that is. We're going from 0 to pi in theta, and 0 to 2 pi in phi, sorry, I'll stick with phi. I think that's actually the more correct Greek pronunciation is phi. So I'll go back and forth. But anyway, it's that letter there. All right. And so you know that just is equal to 4 pi. And then we can look at here and we see, oh, this r squared changed this into an r squared. And so this is what we end up with. We have a 1/2 q squared over 4 pi epsilon 0 squared. I'm writing out, this is this whole quantity squared. I'm writing this out here because you'll also know we just got a 4 pi from here. We have an epsilon 0, so we have a 4 pi epsilon 0 right here. So I'm going to cancel that and cancel that. I'm going to leave this for the moment. You'll see why a little later. Okay, and then all we end up with is we have a 1 over r squared dr integral. And you guys all know that what this gives us is a minus 1 over r. And we are going, of course, we're going from RA to RB. We're looking at this region in here to determine what the capacitance is. And why is that? Well, what's this field out here? 0, right? Okay. So, oh, okay. And this goes from RA to RB. But there's a minus here, so what this ends up being is 1/2 q squared over 4 pi epsilon 0 1 over RA minus 1 over RB. Okay. And that's it. We're done. We're mostly done. This is now U, the energy density in between these two spheres. Well, what else is that? I forgot to moisten this. We'll see what happens. Yeah, we'll go ahead and get rid of this here. Okay, so now we know that's the energy density. That's not the energy density. Sorry. The total energy stored inside the electric field between these two surfaces, the inner sphere and the outer sphere. Well, what else do we know? We know by definition, you guys will remember we just did some really simple algebra. We know by definition that this equals 1/2 q. Got to make sure I have it right. Q squared over c. I'm pretty sure that's right, but actually I need to check that just to be sure. I apologize. Yeah, 1/2 q squared over c. Okay, so this equals 1/2, and I'm just going to pull this up and set these two things equal. You understand, this is the energy density in a capacitor. This is the energy density in this geometry, and we're going to use that to determine what the capacitance is. So we have this over 4 pi epsilon 0, and we have 1 over RA minus 1 over RB. Okay, there we go. We can cancel out the q squared. We cancel out the 1/2, and we need to c we need to bring up, and we have this stuff we need to bring down. So I'm just going to invert both these sides. C equals 4 pi epsilon 0 over the quantity 1 over RA minus 1 over RB. Okay, and let's see, oh, I know what, so we're done. This is it. Your book has a slightly different form, but all they do, and you guys can convince yourself of this, is they multiply the top and bottom of this fraction here, this whole fraction, by RA times RB, and they'll get a different expression right here, but it's the same exact expression. So then the question is, what happens to this as RB? What if this sphere out here, RB, was all the way out at infinity? Well, all the way out at infinity, just keep pushing that thing. What that means is this thing goes to 0, and our new expression for the capacitance of this is 4 pi epsilon 0, 1 over RA, over 1 over RA, which is just times RA. And I'm hoping that's correct. I didn't verify that, but that sure looks like it works out mathematically. So that's a different way of looking at that example in the book. You can use that approach anytime you want. As a matter of fact, you have, what do we have? 3 different expressions for the energy contained within a capacitor. And so you can use any one of those 3 to help you in a specific problem. So That's it. We're done.